What happens when two people invent one thing at once, and neither one knows about the other, and the fight over who was first consumes the rest of their lives and destroys one of them completely? That question sits at the center of the story of calculus. The most powerful mathematical tool ever created was developed independently, within a decade, by two men who could not have been more different. One was a reclusive English physicist who hated criticism so deeply that he hid his greatest work for 20 years. The other was a German polymath, a diplomat and philosopher, who published freely and invented a notation so brilliant that the entire world still uses it 3 centuries later. They arrived at equivalent mathematics from opposite directions. Newton came from physics. Leibniz came from geometry. Newton thought about motion, points moving along curves, velocities changing over time. Leibniz thought about differences, infinitely small gaps between infinitely close points on a curve. Newton's calculus was dynamic, physical, rooted in the real world of falling apples and orbiting planets. Leibniz's calculus was static, algebraic, rooted in the abstract world of symbols and formal manipulation. The fact that these two radically different starting points led to equivalent mathematics is itself one of the most profound facts in the history of the subject. It suggests that calculus is not a human invention shaped by the particular concerns of its inventors. It is a discovery, a mathematical truth that exists independently of the path you take to reach it. Newton and Leibniz took different paths. They arrived at one destination. The destination was there before either of them set out. And then they spent the last decades of their lives trying to destroy each other's reputations over the question of who got there first. The mathematics they created, calculus, is the language of change. It is the tool that describes how things move, how they grow, how they decay, how they curve, how they accumulate. Calculus runs the modern world in ways that are mostly invisible. Every time your GPS calculates a route, it is solving an optimization problem, finding the path that minimizes travel time given current traffic conditions. The algorithm uses derivatives to determine how small changes in the route affect the total time, and it uses that information to improve the route iteratively. Every time your GPS calculates a route, every time a doctor determines a drug dosage, using pharmacokinetic models that describe how drug concentration in your blood changes over time, rising as the drug is absorbed and falling as it's metabolized, with the rate of change at each moment determining the optimal timing and size of the next dose, every time a bridge bears a load without collapsing, every time an airplane stays in the air because its wing was designed using fluid dynamics equations, every time a satellite maintains its orbit because its trajectory was calculated using orbital mechanics, every time an MRI machine reconstructs an image of your brain using Fourier analysis, every time a weather forecast is generated by solving the Navier-Stokes equations on a supercomputer, every time a recommendation algorithm suggests a video by computing gradients in a high-dimensional parameter space, calculus is running underneath, invisible and indispensable. The word underneath is precise. Calculus is not an ingredient in these technologies the way flour is an ingredient in bread. It's the oven. It's the process by which raw materials, data, equations, physical laws are transformed into working systems. Remove the oven, and you can still have flour, but you can't have bread. Remove calculus, and you can still have data, but you can't have the systems that make data useful. The applications are so pervasive that listing them is almost absurd. It would be shorter to list the technologies that don't use calculus. Hammers don't use calculus, spoons don't use calculus, wheelbarrows don't. But anything with a circuit, a sensor, a signal, a model, an optimization, a prediction, or a design that was tested computationally before being built physically, all of those use calculus. The modern world is calculus made physical. This isn't hyperbole, it's a description of how the world actually works. The engineering that keeps buildings standing, the medicine that keeps people alive, the communication that keeps people connected, the computation that keeps the global economy functioning, all of it rests on calculus. And the dependence is not superficial. You can't engineer a bridge without solving differential equations for stress and load. You can't design an aircraft wing without solving the Navier-Stokes equations for airflow. You can't train a neural network without computing derivatives of a loss function. You can't compress an image without Fourier analysis. Remove calculus from the world, and the world doesn't just get worse, it collapses. The entire technological infrastructure of modern civilization is built on the mathematics that two men invented independently in the 17th century, and that a bishop correctly noted had no logical foundation. It is the mathematical foundation of the modern world. We'll follow the idea from Archimedes filling parabolas with triangles in ancient Syracuse, through the plague year that changed everything, through a feud so vicious that the Royal Society rigged its own investigation, through a philosophical attack that exposed the broken foundation underneath, through 2 centuries of repair work, and finally to the machines that learned to think using a 300-year-old rule about derivatives. And the story of how calculus was created, fought over, and nearly broken by its own logical contradictions is what we are going to tell tonight. We'll trace the twin paths of Newton and Leibniz as they converge on one truth from opposite starting points, one from physics, one from geometry, one in secrecy, one in public, and we'll follow the collision when those paths. We'll watch a bishop demolish the foundations. We'll watch 2 centuries of mathematicians rebuild them, brick by logical brick. And we'll follow the thread from Newton's farmhouse to the neural networks that are reshaping civilization, connected by a single mathematical rule about the derivatives of composite functions. All of it, slowly, for sleep. Before we meet Newton and Leibniz, before we follow their parallel paths and their devastating collision, we need to understand what calculus actually does. Not the formulas, not the notation, the idea. The world changes. That is the single most obvious fact about reality, and it is the fact that all of mathematics before calculus was essentially unequipped to handle. Classical mathematics, arithmetic, algebra, geometry, describes things that hold still. The area of a rectangle, the sum of 2 numbers, the angles of a triangle, these don't change. They are static, fixed, eternal. But the real world doesn't hold still. A planet accelerates as it swings around the sun. A population grows slowly, then explosively, then levels off. A drug enters your bloodstream, reaches peak concentration, and then fades. A bridge flexes under wind load. A stock price fluctuates. A neural network adjusts its weights. Everything changes, and the rate of change changes, and the rate of change of the rate of change changes. Calculus is the mathematics of change. It answers 2 questions that no earlier mathematics could answer precisely. First, how fast is something changing at this exact instant? Not on average over an hour, not approximately over a second. Exactly, at this frozen moment in time. Second, how much has something accumulated in total when the rate of accumulation was different at every moment? Not a rough estimate. The exact total. The first question is answered by the derivative, the second by the integral, and the astonishing fact at the heart of calculus, the fundamental theorem, is that these 2 questions are inverses of each other. Answering one automatically gives you the tools to answer the other. The idea behind calculus is older than calculus itself, much older. The idea is this: you can understand something curved, something changing, something continuous, by breaking it into pieces so small that each piece is effectively straight, effectively constant, effectively simple. Then you study the simple pieces. Then you add them back together. And if you use enough pieces, if you let the pieces become infinitely small and infinitely numerous, the sum of the simple pieces gives you the exact answer for the complicated whole. That idea appeared in ancient Greece roughly 2,300 years ago in the work of a mathematician we've met in earlier stories. Archimedes of Syracuse used a technique called the method of exhaustion to calculate areas and volumes that no formula could reach. He filled a parabola with triangles, each one smaller than the last, each one occupying a little more of the remaining space. As the triangles multiplied, the gaps shrank. In the limit, a word Archimedes didn't have, the triangles filled the parabola completely, and the area was exact. Archimedes also calculated the area of a circle by inscribing polygons with more and more sides. A hexagon inside a circle, then a 12-sided polygon, then 24 sides, then 48, then 96. Each polygon was a better approximation of the circle, and the area of each polygon was easy to calculate. As the number of sides increased without bound, the polygon became the circle, and the area became pi times the radius squared. The proof was rigorous, the method was sound, and the result, pi r squared, has been the formula for the area of a circle ever since. But Archimedes went further. He calculated the area under a parabolic segment and proved it equals 4/3 the area of the inscribed triangle. He calculated the surface area and volume of a sphere and proved that the volume is 2/3 the volume of the circumscribing cylinder, a result he was so proud of that he asked for a sphere inscribed in a cylinder to be engraved on his tombstone. He calculated the area of a spiral, and in a work called The Method, lost for centuries and rediscovered only in 1906 on a palimpsest in Istanbul, he described a technique that anticipates integration more directly than anything else in ancient mathematics, a technique involving the balancing of infinitely thin slices of shapes against each other, like putting geometric cross-sections on a lever and finding the point where they balance. The method was Archimedes' private toolkit. He used it to discover results and then proved them separately using the method of exhaustion, which was considered more rigorous. The distinction between discovering a result and proving it, between intuition and proof, is a tension that runs through the entire history of calculus. Newton and Leibniz discovered their calculus through intuition about infinitesimals. It took 2 centuries to prove it rigorously without infinitesimals. The pattern keeps repeating. Insight first, justification later. The method worked. The results were correct. But Archimedes couldn't explain why it worked in a way that satisfied the standards of Greek mathematics. The notion of adding infinitely many infinitely small pieces together to get an exact finite answer was philosophically troubling. How can you complete an infinite process? How can something infinitely small be anything other than nothing? These questions would haunt mathematics for 2,000 years. There is something remarkable about Archimedes' method that is easy to miss. He wasn't approximating. He wasn't saying the area is about this much. He was proving, with geometric rigor, that the area is exactly this value, by showing that any other value leads to a contradiction. If you claim the area is larger than the value he calculated, he can find triangles that contradict you. If you claim it's smaller, he can find triangles that contradict you from the other direction. The true value is the only one that survives both attacks. This technique, squeezing a quantity between 2 bounds that converge to a single value, is the ancient ancestor of the modern concept of a limit. Archimedes was taking limits without having the word, the notation, or the formal definition. He was doing calculus in disguise, using the only language he had, classical Greek geometry. After Archimedes, the idea went quiet. Not because it was forgotten. The thread wasn't entirely lost. Mathematicians across the medieval world continued to push at problems that required something like calculus, even though the full machinery wouldn't exist for centuries. The Babylonians, working roughly 4,000 years ago, tracked the motion of Jupiter across the sky by computing the area under a velocity time graph using trapezoids. They were performing numerical integration to predict planetary positions. In Egypt, the Moscow papyrus records a formula for the volume of a truncated pyramid that is essentially correct and that would, in modern terms, require integration to derive. How the Egyptians arrived at it without integration is one of the enduring mysteries of ancient mathematics. Scholars in the Islamic world and in India continued to develop techniques that resembled calculus in important ways. In Kerala, on the southwestern coast of India, a mathematician named Madhava of Sangamagrama developed infinite series for trigonometric functions in the 14th century, anticipating results that would later be credited to European mathematicians. In Baghdad, the mathematician Ibn al-Haytham worked on problems involving sums of powers that connect to integration. These contributions were real and significant, and they developed independently of the European tradition. The Kerala school deserves particular attention. Madhava and his students, working between the 14th and 16th centuries, developed infinite series for sine, cosine, and arctangent that are identical to series later attributed to Newton, Leibniz, Gregory, and Taylor. They computed pi to 11 decimal places. They developed techniques for accelerating the convergence of slowly converging series. They understood the concept of an infinitely small quantity and used it in ways that closely parallel the European infinitesimal calculus. Whether any of this knowledge reached Europe through trade routes, Jesuit missionaries, or other channels remains debated. No definitive documentary evidence of transmission has been found. but the chronological overlap is striking, and Kerala was a major trading hub with active European contact from the early 16th century onward. The most important point for the story of calculus is this. The Kerala school had many of the pieces but didn't assemble them into a unified system. They had infinite series. They had techniques equivalent to differentiation and integration. But they didn't formulate the fundamental theorem, the recognition that these two operations are inverses. They didn't develop a general-purpose notation, and they didn't create a systematic method applicable to arbitrary problems. The pieces were brilliant. The synthesis was what Newton and Leibniz provided, and the synthesis, the unification of differentiation and integration under one roof, connected by the fundamental theorem, expressed in a powerful notation applicable to arbitrary problems, is what turned calculus from a collection of clever techniques into the universal tool that transformed science and engineering. Whether the Kerala school's lack of synthesis was due to cultural factors, mathematical tradition, the absence of the right notation, or simply the fact that the full synthesis required a particular combination of insights that hadn't converged in 14th century India, is impossible to know. What we know is that the pieces existed, that they were correct, and that they were developed independently of Europe. The history of mathematics is richer for acknowledging this. The question of why calculus wasn't invented sooner, why the gap between Archimedes and Newton is 18 centuries long, has many answers. One is that the algebraic notation needed to express calculus didn't exist until the 16th and 17th centuries. Archimedes worked in geometric language case by case, shape by shape. He couldn't write a general formula because there was no notation for general formulas. Descartes invented the coordinate system. Weierstrass introduced letters for unknowns. Wallace developed the notation for infinite products and series. Each advance in notation brought the synthesis closer. Another answer is that the problems driving the need for calculus didn't fully materialize until the scientific revolution, when Galileo showed that falling objects obey mathematical laws, when Kepler showed that planetary orbits are ellipses. The demand for a mathematics of continuous change became urgent. Astronomers needed to calculate the exact positions of planets at any given moment. Navigators needed to plot courses across oceans, accounting for changing winds and currents. Artillery officers needed to calculate the trajectories of cannonballs through air. Engineers needed to calculate the strength of beams and arches under varying loads. Every one of these problems involved quantities that change continuously, and every one of them was beyond the reach of classical mathematics. The 17th century was a century of motion. The motion of planets, projectiles, ships, machines, and ideas. And motion demands calculus. You can describe static things with arithmetic and geometry. You can describe change only with calculus. The century that discovered the laws of motion also invented the mathematics of motion, and the coincidence was not a coincidence at all. Calculus was invented when it was because the questions it answers became pressing at precisely that moment in history. But the full synthesis, the creation of calculus as a unified system, with general methods, powerful notation, and the recognition that two seemingly different problems are actually one problem seen from opposite sides. That synthesis happened in Europe, in the second half of the 17th century, in the hands of two men whose lives would become permanently entangled. The first was born on Christmas Day, 1642, in a small farmhouse in Lincolnshire, England. His father had died 3 months earlier. He was premature, small enough, his mother reportedly said, to fit inside a quart mug. He grew up solitary, difficult, and brilliant. His name was Isaac Newton. Newton entered Trinity College, Cambridge, in 1661, at the age of 18. He was not a distinguished student at first. He was a sizar, a student who paid for his tuition by serving wealthier students, essentially working as a servant. He made few friends. He kept to himself. He appears to have been deeply unhappy during his first years at Cambridge, writing in a notebook a list of his sins that included threatening to burn down his stepfather's house. Newton's childhood was difficult. His mother had remarried when he was 3, leaving him with his grandmother, and the sense of abandonment marked him permanently. But at Cambridge, something ignited. He was not a distinguished student in the conventional sense. He didn't excel in the standard curriculum of philosophy and theology. But when he encountered mathematics, specifically the work of Descartes, who had recently connected algebra to geometry through the coordinate system, Newton's mind caught fire. He read Descartes' geometry. He read Wallace's Arithmetica Infinitorum. which explored infinite products and series. He read Barry's lectures on optics and geometry. Within 2 years, Newton had absorbed the entire state of mathematical knowledge and was beginning to push past it into territory that nobody had explored. The transformation from unremarkable undergraduate to the greatest mathematician of his generation happened almost entirely in private. Newton didn't discuss his mathematical work with his peers. He didn't seek guidance from his professors, with the partial exception of Barrow. He simply read, thought, and calculated, alone in his rooms at Trinity College, building the foundations of the method of fluxions before anyone knew he was building anything at all. And then, in 1665, the plague came to England. Cambridge closed, students were sent home. Newton returned to Woolsthorpe Manor, the family farmhouse, and spent roughly 18 months in near total isolation. What he produced during those months is among the most extraordinary intellectual achievements in human history. During those 18 months at Woolsthorpe, Newton worked with an intensity that borders on the incomprehensible. He had no collaborators, no research library, no community of scholars to test his ideas against. He had books he'd brought from Cambridge, his own mind, and the silence of a farmhouse during a plague. The plague year is sometimes called Newton's annus mirabilis, his miracle year. The label is warranted. In those 18 months, he not only developed calculus but also performed experiments with prisms showing that white light is composed of a spectrum of colors, began formulating his law of universal gravitation, and made advances in the theory of infinite series. Any one of these achievements would have been the work of a career. Newton produced all of them before his 25th birthday, alone, during a pandemic. The solitude was essential. Newton didn't work well with others. He didn't bounce ideas off colleagues. He didn't collaborate. He thought alone, deeply and obsessively, following a single thread of reasoning until it yielded or broke. The plague gave him the one thing he needed most: uninterrupted time. No lectures to attend, no social obligations, no distractions, no lectures to note. Time. Just Newton and the problems, day after day, for a year and a half. He developed a method for calculating the rate at which a quantity changes at any specific instant, what we now call differentiation. He developed a method for calculating the total accumulation of a quantity that is changing continuously, what we now call integration, and he recognized that these two operations are inverses of each other. Differentiation undoes integration, and integration undegration. Dundesheration. This recognition that finding slopes and finding areas are opposite operations is the fundamental theorem of calculus. It is the single most important insight in the history of the subject, and arguably one of the 10 most important insights in the history of human thought. Before Newton, these were two separate problems with no visible connection, finding slopes and finding areas. One is about the local behavior of a curve at a single point. The other is about the global behavior of a curve across an entire region. One requires zooming in as far as possible. The other requires zooming out and seeing the whole picture. They seem to have nothing in common, and yet they are inverses. Integration undoes differentiation, undoes its differentiation. The local and the global are two sides of one coin. That recognition is the fundamental theorem, and it transformed calculus from two separate collections of techniques into a single unified subject. To appreciate how unexpected this is, consider an analogy. Imagine you discovered that knowing the color of a painting at every single pixel also tells you, automatically, the total weight of the paint on the canvas. Color and weight seem unrelated, but if you knew one, you could calculate the other. That's the level of surprise the fundamental theorem carries. Slopes and areas shouldn't be connected, but they are, and the connection is exact, and it works for every curve, every function, every continuous quantity in the universe. Finding the slope of a curve at a point was a problem in geometry. Finding the area under a curve was a different problem in geometry. Nobody suspected they were related. Newton showed they're inverses of each other. The way multiplication and division are inverses, the way addition and subtraction are inverses. Knowing how to do one instantly gives you the ability to do the other. Here is a concrete way to feel why this is true. Imagine you're tracking a car. You have a function that tells you the car's position at every moment. its distance from the starting point at each instant of time. The derivative of this function gives you the car's speed at each instant. Speed is how fast position is changing. That's the slope problem. Now reverse it. Suppose you know the car's speed at every instant, and you want to figure out how far it has traveled in total. You add up all the tiny distances, speed at each instant multiplied by the tiny duration of that instant, summed across the entire trip. That's the area under the speed curve. That's the area problem. Position gives you speed through differentiation. Speed gives you position through integration. The operations undo each other. The slope of the area function is the original function. The area under the slope function gives back the original function. Two operations, perfectly inverse, connecting two apparently unrelated geometric problems. Isaac Barrow, Newton's teacher at Cambridge, had glimpsed this connection. He proved a geometric version of the Fundamental Theorem before Newton. Barrow didn't take the next step. He didn't create a systematic method for computing derivatives and integrals, didn't develop a notation, didn't build the general-purpose machine that Newton and Leibniz each built. Barrow saw the theorem. Newton and Leibniz built the theory. This is the fundamental theorem of calculus, and it is the insight that unifies the entire subject. To understand what Newton actually created, it helps to understand the two problems that calculus solves. They seem unrelated. They turn out to be inverses of each other. The first problem, given a curve, find its slope at any point. Not the average slope between 2 points, the exact slope at a single point. This is the problem of the tangent line, a line that just touches the curve at one point without crossing it. The slope of that tangent line is the instantaneous rate of change of the curve at that point. Newton wanted to calculate this for any curve at any point exactly. The second problem is the mirror image of the first. Given a curve, find the area enclosed between the curve and the horizontal axis. This is the ancient problem of quadrature, measuring curved regions with straight-edged tools. Archimedes attacked it with triangles. The Babylonians attacked it with trapezoids. The question is as old as geometry. How much space does a curved shape enclose? The answer, in general, requires adding up infinitely many infinitely thin vertical strips, each one extending from the horizontal axis to the curve. Each strip has a width of essentially 0 and a height determined by the curve. The area of each strip is essentially 0, and the sum of infinitely many essentially 0 areas is a finite number. This seems paradoxical, and it is paradoxical until you formalize it with limits. The integral is the limit of a sum of thin rectangles as the rectangles become infinitely thin and infinitely numerous. The limit exists, it's finite, and it gives the exact area. The second problem, given a curve, find the area enclosed between the curve and the horizontal axis. This is the problem of quadrature, Archimedes' problem, the problem of measuring shapes with curved boundaries. Newton wanted to calculate this for any curve, over any interval exactly. The connection between these two problems is not obvious. One is about slopes, the other is about areas. One is local, it asks about a single point. The other is global, it asks about an entire region. They seem to live in different mathematical universes. Newton showed they live in one universe. The slope problem and the area problem are inverses of each other. If you solve the area problem and then take the slope of the answer, you get back the curve you started with. If you solve the slope problem and then compute the area under the answer, you get back the curve you started with. Slopes undo areas, areas undo slopes. The two problems cancel each other out, the way addition cancels subtraction. This is the fundamental theorem of calculus, and it is the most important single idea in the subject. Newton called his method the method of fluxions. A fluxion was a rate of change, essentially a derivative. He thought of mathematical curves as being traced by moving points, and he was interested in the velocity of those points at each instant. His calculus was physical, grounded in motion. A curve wasn't a static shape. It was a trajectory, a record of something moving through space over time, and the fluxion was the speed of that motion at any given moment. Think about what this means physically. If you throw a ball in the air, its height changes over time. At first, the ball rises quickly. Then it slows down, stops for an instant at the peak, and falls back, accelerating downward. At every moment, the ball has a specific height and a specific speed. The height is the position. The speed is the rate of change of position. The speed is the derivative change of position. The speed is the derivative. But the speed itself also changes. At the bottom of the throw, the speed is high. At the peak, the speed is zero. The rate at which speed changes is called acceleration, and acceleration is the derivative of speed, which makes it the second derivative of position. Newton's second law, force equals mass times acceleration, is a statement about the second derivative of position. The deepest law of classical mechanics is a relationship between a function and its second derivative, and you need calculus to even state it precisely. Let alone solve it. This is why calculus was not just useful for physics. It was necessary. Without calculus, Newton's laws of motion cannot be written down. Without the derivative, there is no precise concept of instantaneous velocity. Without the integral, there is no way to reconstruct position from velocity. The physics and the mathematics were born together because neither could exist without the other. The method of fluxions gave Newton the power to solve problems that had been impossible for millennia. Given any curve described by an algebraic expression, he could find the slope at any point. Given any changing quantity, he could find its instantaneous rate of change. And given any rate of change, he could reconstruct the original quantity by integration. Consider what this meant in practice. Galileo had shown that a falling object covers a distance proportional to the square of the time it has been falling. Newton could differentiate this function and get the velocity at each instant. Differentiate again, and he got the acceleration, constant, equal to the gravitational acceleration. He could work backward too. Given the acceleration, he could integrate to get the velocity, and integrate again to get the position. The equations of motion, which Galileo had discovered empirically, Newton could now derive mathematically. An identical technique applied to planetary orbits. Kepler had discovered that planets move in ellipses, but he didn't know why. Newton showed that an inverse square force law, the gravitational force decreasing as the square of the distance, produces exactly the elliptical orbits Kepler had observed. The derivation required calculus at every step, setting up the differential equation of motion, solving it using integration, and extracting the orbital shape from the solution. Without calculus, the connection between gravity and elliptical orbits is invisible. With calculus, it's inevitable. With calculus, it's inevitable. Newton didn't develop calculus in a vacuum. He developed it because he needed it. He needed it to solve the deepest problem in physics, the motion of the planets. The connection between calculus and astronomy is the thread that runs through the entire first century of the subject's existence. Kepler, working from the astonishingly precise astronomical observations of the Danish astronomer Tycho Brahe, had discovered that planets move in ellipses with the sun at one focus, that they sweep out equal areas in equal times, and that the square of the orbital period is proportional to the cube of the semi-major axis. These three laws were empirical. They described what planets do without explaining why. Newton wanted the why. The answer required calculus at every step. Newton had to set up a differential equation describing the motion of a planet under an inverse square gravitational force. He had to solve the equation, which meant integrating, finding the function whose derivative satisfied the equation, and the solution turned out to be an ellipse. Kepler's first law dropped out of Newton's mathematics as a consequence of universal gravitation combined with calculus. The second and third laws followed similarly. Equal areas in equal times is a consequence of the conservation of angular momentum, which Newton derived using calculus. The relationship between period and distance follows from integrating the orbital equation over one complete revolution. Every result that Kepler had painstakingly extracted from observational data, Newton derived from a single assumption, the inverse square law of gravity, plus the mathematical machinery of calculus. The empirical became theoretical, the descriptive became explanatory, and the tool that made the transformation possible was the method of fluxions. Newton compiled these results in his Principia Mathematica, published in 1687, one of the most important books in the history of science. The publication happened because of the astronomer Edmund Halley. In 1684, Halley visited Newton in Cambridge to ask a question that had been puzzling several prominent scientists. What shape would a planet's orbit be if the gravitational force decreased as the square of the distance? Newton answered immediately, an ellipse. He had proved it years ago, during the plague year. Halley, stunned, asked to see the proof. Newton couldn't find it among his papers but promised to recreate it and send it to Halley. What Newton sent was not just the proof, it was the beginning of the Principia, a systematic derivation of the laws of motion and gravitation that grew, over the next 2 years, into a 3-volume masterwork. Halley edited the manuscript, resolved a priority dispute between Newton and Robert Hooke that nearly caused Newton to withdraw the work, and paid for the publication out of his own pocket when the Royal Society ran out of funds. The Principia was published in 1687, one of the most important books in the history of science. The Principia used calculus throughout, but disguised it in geometric language, presenting results as geometric constructions rather than algebraic derivations. Newton may have done this because he considered geometric proofs more rigorous, or because he wanted to make the work accessible to mathematicians who didn't know his Fluxion methods, or because he wanted to conceal his methods from potential rivals. Probably all three. The mathematics was revolutionary, but Newton didn't publish it. He wrote it up. He shared it with a small circle of trusted colleagues. It appeared implicitly in his masterwork, the Principia Mathematica, published in 1687. But he never published his calculus as a standalone work during the years when it would have established his priority beyond dispute. He sat on it for over 20 years. The greatest mathematical discovery since Euclid's Elements, arguably the most powerful intellectual tool in human history, sat in Newton's desk for 2 decades because its creator was afraid someone might disagree with it. The irony is considerable. Newton was the most brilliant mathematician of his generation, possibly of any generation. His work was so far ahead of his contemporaries that there was essentially nobody alive who could have offered a meaningful critique. The criticism he feared was not criticism that could have improved the work. It was criticism that would have annoyed him, and Newton's tolerance for annoyance was approximately 0. He once described criticism of his work as being like having his fingers scraped with a sharp edge. The physical metaphor is telling. Newton experienced intellectual disagreement as physical pain. Publishing meant exposing himself to that pain, and he would rather sit on the most important mathematical discovery in history than endure it. The personality that made Newton a great scientist, the obsessive focus, the refusal to accept approximate answers, the willingness to sit with a problem for months or years until it yielded, was inseparable from the personality that made him a difficult colleague and a vindictive opponent. That intensity that drove him to solve the greatest problems in physics, drove him to pursue his enemies with relentless fury. That mind created the Principia. That mind drafted the Commercium Apollicum. Newton was not 2 people. He was 1 person, and his virtues and his flaws grew from 1 root. This personality trait, the combination of supreme confidence in his own abilities and extreme sensitivity to any challenge, defined Newton's entire career. He picked fights with Robert Hooke over optics. He picked fights with John Flamsteed over astronomical data. He picked fights with Leibniz over calculus. And in every case, the fight consumed enormous amounts of time and energy that could have been spent on mathematics. Newton was his own worst enemy, not because he lacked talent, but because his temperament converted every professional interaction into a potential conflict. Why? Newton was terrified of criticism. His early work on optics had drawn objections from Robert Hooke and others, and the experience had been so unpleasant that Newton essentially withdrew from public scientific discourse. He described the experience as being persecuted and resolved never again to expose his ideas to public scrutiny until they were so thoroughly developed that no objection could touch them. This decision, born of anxiety, not strategy, would have consequences that neither Newton nor anyone else could have predicted, because while Newton was sitting on his calculus in the quiet of Cambridge and later London, a man in Germany was independently developing equivalent mathematics from a completely different starting point. Gottfried Wilhelm Leibniz was born in Leipzig in 1646, 4 years after Newton. He was Newton's opposite in almost every respect. If Newton was a laser, intense, focused, and capable of burning through a single problem for months, Leibniz was a searchlight, sweeping across entire fields of knowledge, illuminating connections that nobody else could see. Leibniz was a polymath in the deepest sense. He invented a mechanical calculator that could multiply and divide, decades before anything comparable existed. He developed binary arithmetic, the system of ones and zeros that now underlies every digital computer. He made original contributions to philosophy that influenced Kant, Hegel, and Russell. He designed a system of symbolic logic that anticipated modern mathematical logic by 2 centuries. He served as a diplomat, a historian, and a legal advisor to the House of Hanover. He corresponded with over 1,000 people across Europe, maintaining an intellectual network that was effectively the internet of the 17th century. And yet, despite this astonishing range, Leibniz was often underestimated by his contemporaries. He held no university position. He was a courtier, dependent on the patronage of the House of Hanover, the German noble family that would, in an ironic twist, ascend to the British throne in 1714 as George I. Just 2 years before Leibniz died, Leibniz had spent decades serving the Hanovers, researching their genealogy, advancing their political interests, and hoping for a position in London when they became the British royal family. The position never materialized. George I came to England and left Leibniz behind in Hanover, apparently considering him more of a liability than an asset in the politically charged atmosphere of the Newton-Leibniz dispute. His mathematical work was done in stolen hours between diplomatic missions and administrative duties. The calculus, arguably his greatest intellectual achievement, was produced not in the quiet of an academic study, but in the margins of an incredibly busy life. Where Newton was reclusive, Leibniz was sociable. Where Newton was focused on physics, Leibniz ranged across philosophy, law, diplomacy, history, linguistics, and theology. When Newton guarded his work jealously, Leibniz published freely and corresponded with hundreds of scholars across Europe. Leibniz didn't begin serious mathematical study until his mid-20s, late by the standards of mathematical prodigies. In 1672, while on a diplomatic mission to Paris, he met the Dutch mathematician Christian Huygens, who recognized Leibniz's potential and gave him a reading list that would change his life. Huygens was one of the foremost scientists in Europe. He had discovered the rings of Saturn, invented the pendulum clock, and developed a wave theory of light. He was also a generous teacher who took Leibniz seriously despite his mathematical inexperience. The reading list included works by Pascal, Descartes, Gregory of St. Vincent, and others. Leibniz worked through them with extraordinary speed, annotating and any ideas he encountered. Within 2 years, he had mastered the state of the art. Within 3, he had surpassed it. The speed of his mathematical development remains one of the most impressive feats of autodidactic learning in the history of the subject. Leibniz caught up with remarkable speed. He was not a mathematical prodigy. He came to the subject late, driven by curiosity rather than childhood talent. But he had an extraordinary ability to absorb, synthesize, and extend ideas. He read voraciously, corresponded with every major mathematician in Europe, and had a capacity for sustained abstract thought that rivaled Newton's, though it expressed itself very differently. When Newton dove deep into a single problem and stayed there until it yielded, Leibniz ranged across many problems simultaneously, making connections that specialists missed. Within 3 years, he had developed the core of his own calculus. When Newton thought of curves as trajectories and fluxions as velocities, Leibniz thought of curves as geometric objects and differentials as infinitely small differences. His approach was algebraic and notational rather than physical. He was interested in the formal manipulation of symbols, in creating a calculus, literally a system of calculation, that could be applied mechanically to any problem. And his notation was superb. In 1675, Leibniz introduced the elongated S symbol for integration, from the Latin word summa, meaning sum. He introduced the notation d over dx for the derivative. He introduced the d for differential, giving us dx and di as the building blocks of his system. Leibniz spent years thinking about notation before settling on his system. He understood, more deeply than Newton or perhaps anyone else of his era, that good notation doesn't just record ideas. Good notation thinks for you. The right symbols, arranged in the right way, make correct manipulations feel natural, and incorrect manipulations feel wrong. Notation is a tool for the hand that thinks with the mind. The notation was designed to be manipulated. You could treat d over dx as if it were a fraction, cancel terms, rearrange expressions, and the results came out correct. For example, if you know that d's over dt equals v, that the rate of change of position with respect to time equals velocity, then you can separate variables by writing ds equals v dt, and then integrate both sides to get the total distance. The notation does the algebra for you. Newton's dot notation does the mathematician, because the dots are attached to the variable and don't separate. Leibniz's integral sign, the elongated s, visually represents what integration does. Summing. The symbol tells you the operation. The dx at the end of an integral tells you the variable of integration and reminds you that you're summing infinitely many thin slices, each of width dx. Every piece of the notation encodes a piece of the meaning. The notation didn't just record the mathematics, it did the mathematics for you. Newton's notation, by contrast, used dots above letters to indicate rates of change. It was adequate for physics, but clumsy for pure mathematics. It didn't generalize well. It didn't invite the kind of formal manipulation that Leibniz's notation encouraged. And this difference in notation had lasting consequences for the development of mathematics in England versus the continent. For roughly a century after the feud, English mathematicians stubbornly used Newton's dot notation out of national loyalty, while continental mathematicians used Leibniz's notation because it was better. The result was that continental mathematics, particularly in France, Switzerland and Germany, advanced far more rapidly than English mathematics during the 18th century. The Bernoullis, Euler, Lagrange, Laplace, all continental, all using Leibniz's notation, all pushing calculus into new territory at a pace that the English couldn't match. It wasn't until the early 19th century when a group of Cambridge students called the Analytical Society campaigned to replace Newton's notation with Leibniz's in English universities that Britain caught up. Charles Babbage, one of the Society's founders, described their mission as promoting the principles of pure deism as opposed to the dot age of the university. The pun tells you everything about how seriously they took the notation question. Babbage, John Herschel, and George Peacock founded the Analytical Society in 1812, specifically to reform mathematical notation at Cambridge. They translated and published Lacroix's textbook on differential calculus, which used Leibniz's notation, and they campaigned for its adoption in Cambridge examinations. The reform met fierce resistance from Cambridge traditionalists, who viewed Leibniz's notation as a continental import that dishonored Newton's memory. The debate was conducted in terms that mixed mathematics with nationalism, which is never a productive combination. But the reformers were right. Leibniz's notation was objectively superior for mathematical work, and clinging to Newton's notation out of patriotic loyalty was holding British mathematics back. The reform took decades, but eventually succeeded, and by the mid-19th century, Leibniz's notation was standard throughout Britain. The episode illustrates something deep about mathematics. Notation isn't superficial, it shapes thought. When you write d over dx, the notation invites you to treat the derivative as a ratio, to cancel terms, to separate variables, to manipulate the expression algebraically. When you write y dot, the notation invites none of these things. The same mathematics, expressed in different notation, leads to different insights, different methods, and different speeds of development. This is why Leibniz's contribution to calculus is as important as Newton's, even though Newton got there first. Newton invented the mathematics. Leibniz invented the language. And the language turned out to be at least as important as the mathematics, because the language is what allows other people to use the mathematics efficiently. Newton was a genius. Leibniz was also a genius. But the world doesn't run on genius. It runs on tools that ordinary people can learn to use. And Leibniz's notation was a better tool, easier to learn, easier to apply, easier to extend to new problems. This is a general principle that applies far beyond calculus. The most important innovations in mathematics are often notational, not conceptual. The Hindu-Arabic numeral system, algebraic numeral system, algebraic notation, the equals sign, the function notation f of x. Each of these made existing ideas accessible to a wider audience and enabled calculations that were previously impractical. Leibniz understood this. He spent more time thinking about notation than any mathematician before him, and his investment paid dividends for 3 centuries. Leibniz published his calculus in 1684 in a paper titled Nova Methodus pro maximis et minimis, a new method for maxima and minima. The paper was dense and difficult to read, but it was public, it was available, and the mathematical community in continental Europe picked it up immediately. The Bernoulli brothers, Jakob and Johann, became Leibniz's champions, extending and applying his methods to an astonishing range of problems. Newton had developed his calculus nearly 20 years earlier, but had published nothing. The stage was set for a disaster. The collision began slowly, and then accelerated into one of the ugliest episodes in the history of science. The Principia used calculus throughout, but presented it in a geometric disguise, avoiding the fluxion notation and expressing results in the language of classical geometry. Readers could see that powerful new methods were at work, but the methods themselves were not laid bare. Leibniz, reading the Principia, recognized some of the underlying ideas, but also saw that his own approach was different in conception, notation, and style. For roughly 15 years after Leibniz published his calculus, the relationship between the two men was civil, even collegial. Newton acknowledged Leibniz in the Principia, noting that Leibniz had fistia, mating that Leibniz had independently arrived at similar methods. Leibniz praised Newton publicly and privately. The mathematical community treated them as co-discoverers of a great new method, and the coexistence seemed stable. For a while the two men were cordial. They exchanged letters. Newton acknowledged Leibniz's contributions. Leibniz praised Newton's achievements. The mathematical community treated them as independent discoverers of related methods. This peaceful coexistence lasted roughly a decade. Then the accusations began. In 1704, Newton published his Optics, which included an appendix on his method of fluxions. The first time his calculus appeared in print as a standalone treatment. In the appendix, Newton included pointed remarks suggesting that his methods predated Leibniz's by many years. Leibniz, reading these remarks, felt accused. He wrote a review in which he suggested that Newton had borrowed ideas from him. Newton, reading the review, was furious. The dispute escalated with the peculiar viciousness that only intellectual priority disputes can generate. This wasn't a disagreement about ideas. Both men agreed that the calculus was correct. The argument was about credit, about who deserved to be remembered as the creator of the most important mathematical tool since geometry. For men of their stature, in an era when scientific reputation was inseparable from personal honor, the stakes were existential. The dispute escalated through intermediaries, through published pamphlets, through letters that were shown to allies and then leaked. Each side recruited supporters. The English mathematical community rallied behind Newton. The continental community rallied behind Leibniz. Mathematics itself became a proxy war between England and the rest of Europe. In 1712, the Royal Society of London, the most prestigious scientific institution in England, convened an official committee to investigate the priority question. The committee produced a report concluding that Newton had developed his calculus first, and that Leibniz had likely derived his methods from Newton's unpublished manuscripts. The report was presented as the result of an impartial investigation. It was written by Newton himself. This is not a rumor or an inference. Newton's drafts of the committee report survive in the archives. The handwriting is his. The selection of evidence was his. The framing of every conclusion was his. He controlled the investigation from beginning to end, while presenting it to the public as an objective inquiry conducted by impartial judges. Some of the committee members may not have known the full extent of Newton's involvement. Others certainly did. But Newton was the most powerful man in English science, President of the Royal Society, Warden of the Royal Mint, a Knight of the Realm, and challenging him was professionally dangerous. The investigation proceeded as Newton directed, and the report concluded as Newton wished. The report was published in 1712 under the title Commercium Epistolicum. It presented a selective collection of letters and manuscripts designed to establish Newton's priority. Letters that supported Newton's case were included. Letters that complicated it were omitted. The presentation was one-sided in a way that modern historical analysis has thoroughly documented. He was the president of the Royal Society at the time. He drafted the committee's conclusions, selected the evidence to be presented, and orchestrated the entire proceeding while maintaining the fiction of impartiality. It was an act of institutional power wielded in the service of personal vindictiveness, and it cast a shadow over Newton's reputation that has never fully lifted. Leibniz was devastated. He spent his final years defending himself against charges of plagiarism, writing letters and counter-arguments, trying to rally support. He died in 1716 in Hanover, Germany, largely abandoned by his patrons and his colleagues. His funeral was attended by his secretary and almost nobody else. One observer noted that he was buried like a highway robber, with minimal ceremony and no honours. The contrast with Newton's death 11 years later is painful. Newton received a state funeral. He lay in state in Westminster Abbey. His pallbearers included dukes, 3 earls, and the Lord Chancellor. His tomb in Westminster Abbey is one of the most elaborate in the entire building. He was celebrated as the greatest scientist in history. Leibniz, whose notation the world uses, whose approach the world follows, whose philosophical framework influenced Kant and Russell and Wittgenstein, was buried in an unmarked grave. The grave was lost for 50 years. When it was finally located, a monument was erected, but it took until the 20th century for the full extent of Leibniz's contributions to be recognized by historians of mathematics. The injustice of Leibniz's treatment is compounded by the fact that it was, in large part, Newton's doing. Newton used his institutional power to damage Leibniz's reputation and his career. The Commercium Epistolicum, the rigged investigation, the anonymous reviews that Newton wrote attacking Leibniz. All of these contributed to the perception that Leibniz was a plagiarist, a perception that persisted for over a century after both men were dead. The rehabilitation of Leibniz's reputation is one of the great corrections in the history of science. It required careful examination of manuscripts, letters, and working papers, conducted by historians who could reconstruct the chronology of each man's work independently. The conclusion is now beyond dispute. Leibniz developed his calculus independently, from different starting points, using different methods, arriving at equivalent results. The coincidence is not suspicious. It is the natural consequence of two extraordinary minds working on problems that were ripe for solution. The consensus of modern historians is clear. Newton and Leibniz developed calculus independently. Newton got there first, chronologically, developing his method of fluxions in 1665 and 66. Leibniz developed his calculus independently, starting around 1673 and published first in 1684. They came from different intellectual traditions, approached different problems, and developed different notations. The fact that their methods turned out to be mathematically equivalent is not evidence of theft. It is evidence that they were both chasing one deep mathematical truth, and the truth was ready to be found. And the cruelest irony of all, Leibniz's notation won. The dx, the di, the integral sign, the di over dx, that's all Leibniz. Newton's dot notation survives in some corners of physics, but was largely abandoned for mathematical purposes within a century of his death. The entire world learned calculus in Leibniz's language, not Newton's. The man who was buried like a robber won the war of notation, and notation is what endures. The consequences of the feud extended far beyond the personal. Because Newton was English and Leibniz was German, the dispute split European mathematics along national lines. English mathematicians, out of loyalty to Newton, used his notation and his methods. Continental mathematicians used Leibniz's notation and developed his approach. For roughly a century, there was almost no mathematical communication between England and the continent. This isolation devastated English mathematics. The great advances of the 18th century, the work of Euler, Lagrange, Laplace, the Bernoullis, happened on the continent, using Leibniz's tools. English mathematicians, hobbled by inferior notation and cut off from the most creative mathematical community in Europe, fell a generation behind. The country that produced Newton, arguably the greatest mathematician who ever lived, spent the century after his death in mathematical decline because his feud with Leibniz poisoned the well. It is one of the most dramatic examples in the history of science of how personal conflict can damage the enterprise of knowledge. The calculus didn't care about the feud, but the mathematicians did, and the mathematics suffered for it. If you're drifting off, that's fine. The feud burned itself out 300 years ago, and the mathematics survived both men. The derivatives don't care who invented them. The integrals don't remember the accusations. What remains is the calculus itself, and it works regardless of whose name is attached to it. Both Newton and Leibniz relied on quantities that were infinitely small but not zero. Newton's fluxions depended on evanescent increments, quantities that were vanishing but hadn't quite vanished. Leibniz's differentials, dx and d, were infinitely small changes in x and y, smaller than any finite quantity but somehow still present, still participating in the mathematics. The trouble is obvious once you state it plainly. Is dx 0 or isn't it? If dx is 0, then di over dx is 0 divided by 0, which is undefined. You can't divide by 0. The entire edifice of differential calculus rests on a fraction whose denominator is 0. That can't be right. But if dx isn't 0 if it's some very small but positive quantity, then the derivative you calculate isn't exact. It's an approximation. And calculus was supposed to give exact answers, not approximations. The whole point was precision. Newton tried to resolve this by talking about ultimate ratios, the ratio of two vanishing quantities at the moment they vanish. But what is a ratio at the moment both quantities are 0? That's still 0 over 0. The language changed, the problem didn't. Leibniz was more comfortable with the contradiction. He treated infinitesimals as useful fictions, quantities that don't truly exist but that produce correct results when manipulated according to certain rules. He was pragmatic when Newton was anxious. But pragmatism isn't a foundation. It works isn't a proof. In 1734, a bishop named George Berkeley published a pamphlet called The Analyst that attacked the logical foundations of calculus with devastating precision. Berkeley was no mathematician. He was a philosopher, a theologian, and eventually a bishop of Cloyne in Ireland. His target wasn't mathematics per se. He was arguing that if mathematicians mocked religious believers for accepting things on faith, they should examine their own foundations with equal skepticism. The infinitesimals, Berkeley argued, were no more logically defensible than the mysteries of religion. Mathematicians were asking the public to trust results derived from entities that were simultaneously 0 and not 0, existent and non-existent, alive and dead. But he could spot a logical contradiction, and the foundations of calculus were riddled with them. Berkeley called infinitesimals ghosts of departed quantities, a phrase so perfectly constructed that it has survived for 3 centuries. His pamphlet, The Analyst, was addressed to an infidel mathematician, likely Edmund Halley, the astronomer who had funded Newton's Principia, and who was reportedly skeptical of religious faith. Berkeley's argument was, in essence, you mock religious believers for accepting mysteries on faith, but your own calculus rests on mysteries just as profound and just as unjustified. His argument was precise. Mathematicians who used calculus first assumed that an increment was non-zero, divided by it, and then set it to 0 when it was convenient to do so. They were having it both ways. The increment was alive when they needed it, and dead when they didn't. Ghosts of departed quantities. The mathematical community had no good answer to Berkeley's objection. The calculus worked. Every result it produced could be verified by other means. Bridges stood, orbits were predicted, projectile trajectories were calculated correctly, but the logical foundation was broken. Consider what a derivative actually requires you to do. You want to find the slope of a curve at a single point, but a slope requires 2 points. Rise over run. The difference in height divided by the difference in horizontal distance. At a single point, there is no rise and no run. The slope at a single point is 0 divided by 0, which is undefined. So you cheat. You pick 2 points very close together on the curve and calculate the slope of the line connecting them. This gives you an approximation to the slope at the point. Then you move the 2 points closer together. The air clove the capote. Closer still. Better still. You imagine the 2 points getting infinitely close, the gap between them shrinking to nothing, and you ask, what slope are you approaching? That's the limit. The derivative is the limit of the slope between 2 points as the distance between them approaches 0. The limit is what you're heading toward, not what you arrive at. You never actually reach 0 distance. You approach it, and the value you approach is the derivative. The brilliance of this concept is that it sidesteps the 0 over 0 problem entirely. You never divide by 0. You divide by smaller and smaller positive numbers and watch what happens to the answer. If the answer stabilizes, if it approaches a specific value and stays near that value no matter how small you make the denominator, then that specific value is the derivative. This works. It produces correct answers It can be formalized precisely, but it took over a century after Newton and Leibniz for mathematicians to find the right formalization. In the meantime, they used infinitesimals, which worked but couldn't be justified. The tool was reliable but unexplained, like a medicine that cures the disease but nobody knows why, or like a bridge that holds weight but whose blueprints, when examined closely, contain an impossible step. The bridge works, the step is impossible. Both statements are true. Reconciling them would take the efforts of some of the finest mathematical minds of the 19th century. If you are drifting, let the ghosts of the departed quantities drift with you. They haunted mathematics for over 100 years, and they were eventually laid to rest by a definition so precise that it left no room for ghosts. But the rest came later. For now, the ghosts were real, and the calculus worked anyway. Bridges stood on ghostly foundations. Planetary orbits were predicted by ghostly arithmetic. The heat flowing through a metal bar was calculated using ghostly infinitesimals. The ghosts didn't care that they were philosophically incoherent. They showed up, did the work, and vanished before anyone could pin down what they were. And the buildings they built didn't fall down. That fact, that a logically broken method produced physically correct results consistently for over a century, is itself one of the great mysteries in the history of mathematics. Why should a method that can't be justified logically produce results that can be verified experimentally? The answer, which Cauchy and Weierstrass would eventually provide, is that the method isn't actually broken. It's just described in the wrong language. The infinitesimals are a metaphor for a limit process that is perfectly rigorous when stated correctly. The ghosts aren't ghosts, they're limits wearing costumes. The situation was genuinely scandalous if you cared about logical foundations, and some people did. Other mathematicians, sympathetic to calculus but troubled by its foundations, tried various fixes. Some proposed that infinitesimals were not numbers but a new kind of quantity, something between 0 and any positive number. Others proposed that the derivative should be understood as the ratio of two specific finite quantities, chosen according to specific rules. Others simply ignored the problem and kept calculating, on the grounds that the results were correct and the philosophical questions could wait. The philosopher Voltaire, who was no mathematician but a keen observer of intellectual culture, noted the contradiction with characteristic wit. He described calculus as the art of numbering and measuring exactly a thing whose existence cannot be conceived. The situation was culturally peculiar. Calculus was being used to design warships, predict eclipses, calculate insurance premiums, and model the orbits of comets, practical applications of enormous importance. And the theoretical foundation was an acknowledged mess. The practitioners didn't care. The philosophers did. The split between those who cared about results and those who cared about foundations would persist throughout the 18th century and into the 19th, until the foundation was finally fixed. The mathematicians couldn't define what they were doing, but they could do it brilliantly, and the results kept working. This situation, a working tool with a broken foundation, persisted for over a century. Mathematicians used calculus freely, extending it, applying it, building the modern world with it. But the foundational question remained: what exactly are we doing when we take a derivative? What exactly is an infinitesimal? How can we add infinitely many infinitely small things and get a finite answer? The resolution came slowly, over the course of the 19th century, through the work of several mathematicians who rebuilt calculus from the ground up without infinitesimals. The first major step was taken by the French mathematician Augustin Louis Cauchy in the 1820s. Cauchy was one of the most important mathematicians of the 19th century and one of the most prolific. He published over 800 papers, second only to Euler in output. He was a complicated figure, politically conservative, deeply Catholic, and occasionally insufferable to his colleagues. He was also extraordinarily productive, publishing at a rate so prolific that the French Academy of Sciences imposed a page limit on its journal specifically to slow Cauchy down. The limit is still in effect. He worked on virtually every branch of mathematics, but his most lasting contribution was bringing rigor to analysis. The branch of mathematics that includes calculus. Cauchy replaced the vague notion of approaching a limit with a precise definition. A sequence approaches a limit L if, for any degree of closeness you specify, no matter how tiny, the sequence eventually stays that close to L and never wanders away again. No matter how tight the tolerance, the sequence eventually meets it and keeps meeting it forever after. This definition uses only finite quantities. There are no infinitesimals. There are no infinitely small numbers. There are only ordinary numbers, epsilon and the terms of the sequence, and the relationships between them. The infinite process is still there. The sequence has infinitely many terms, but the definition describes it using purely finite language. That was Cauchy's key innovation. He found a way to talk about infinite processes without invoking infinite quantities. The key insight is that you never need to talk about infinitely small quantities. You talk about ordinary, finite quantities that can be made as small as you like. As small as you like is different from infinitely small. It's a finite process with no limit on how far it can go, rather than an infinite quantity that somehow exists. Cauchy's work was a major advance, but it still contained some imprecisions. Cauchy's work was a major advance, but it still contained gaps. He sometimes appealed to intuitive notions of continuity and convergence that he hadn't fully defined. He also made errors that his own framework should have prevented. He claimed, incorrectly, that a convergent series of continuous functions is always continuous, a mistake that later mathematicians would correct. The full rigorization was completed by the German mathematician Carl Weierstrass in the 1860s and 70s. Weierstrass formulated what is now called the epsilon-delta definition of a limit, a definition so precise that it eliminates every trace of vagueness and every appeal to intuition. The definition works like this. We say that the limit of a function f of x as x approaches a value a equals L if for every positive number epsilon, no matter how small, there exists a positive number delta such that whenever x is within delta of a, but not equal to a, if of x is within, in symbols for all epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus a is less than delta and greater than 0, then the absolute value of f of x minus L is less than epsilon. Read that again slowly. It says, you challenge me with a tolerance, epsilon. You say, prove that f of x gets within epsilon of L, and I respond with a region, delta. I say, look at all the x values below the epsilon. Every single one of them maps to an f of x value within epsilon of L, and this works for every epsilon you could possibly choose, no matter how small. That's what for all epsilon means. Every tolerance, every challenge, I can always meet it. No infinitesimals, no infinitesimals, no infinitesimals, no infinitesimal, no encroaching, just ordinary numbers and the relationships between them. The definition is purely logical, purely finite, and completely rigorous. When I first encountered the epsilon-delta definition in a university course, I hated it. It seemed like an unnecessarily complicated way to say something simple. A limit is what a function approaches. Why do you need all those symbols, all those quantifiers, all those nested conditions? Why can't you just say what you mean? It took me months to understand that the symbols are what you mean. The English sentence, a function approaches a value, is ambiguous. Different people interpret it differently. The epsilon-delta definition is not ambiguous. It says exactly one thing, and it says it with a precision that natural language cannot match. The complexity isn't decoration. It's the price of clarity. And once you pay that price, the rewards are enormous. Every theorem you prove using the definition is bulletproof. No counterexample can touch it. No philosophical objection can undermine it. The foundation holds. The epsilon-delta definition is widely regarded as one of the most important intellectual achievements in the history of mathematics. It solved a problem that had been open for 200 years. It justified every calculation that Newton and Leibniz and their successors had made, without relying on the logically questionable infinitesimals. It turned calculus from a collection of brilliant tricks into a mathematically sound structure built on provable foundations. The ghost of the infinitesimal was finally exorcised. Every calculation that Newton and Leibniz and their successors had performed, every derivative, every integral, every solution to a differential equation could now be justified without any appeal to quantities that are simultaneously 0 and not 0. The building stood, and now the foundation stood too. Weierstrass worked at the University of Berlin and attracted students from across Europe and America. He never published a comprehensive textbook of his methods. His influence spread primarily through his lectures, which were attended by mathematicians who then carried his ideas to their own institutions. The rigorization of calculus was transmitted orally, from teacher to student, in a chain of mathematical education that continues to this day. Every calculus student who encounters the epsilon-delta definition is receiving, through a chain of teachers stretching back to Berlin in the 1860s, the precision that Weierstrass fought to establish. But it came at a cost. The epsilon-delta definition is hard. It's abstract. It requires a kind of logical precision that is foreign to most people's mathematical intuition. Students who encounter it for the first time often find it impenetrable, a wall of quantifiers and inequalities that seems designed to obscure rather than clarify. The irony is real. The definition that finally made calculus logically sound is the definition that makes calculus hardest to learn. There is a cruel irony in this. Calculus was created by geniuses who relied on intuition. It was rigorized by other geniuses who replaced intuition with precision. And now it is taught to students who are expected to master both the intuition and the precision simultaneously, which is roughly like being asked to learn to swim and to understand the physics of fluid dynamics simultaneously. Most students encounter calculus as a collection of rules: power rule, product rule, chain rule, integration by parts. They memorize the rules, apply them to exercises, and pass or fail the exam. The conceptual understanding, what a derivative actually is, what an integral actually means, why the fundamental theorem is shocking, often comes later or not at all. And the rigorous foundation, the epsilon-delta definitions, the proofs of the basic theorems, comes later stiller, typically in a real analysis course that most students never take. This means that the vast majority of people who know calculus know it as a collection of techniques without a conceptual foundation and without a logical justification. They can differentiate x squared and integrate sine of x, but they can't explain what a limit is, and they couldn't define continuous if their life depended on it. They are in Newton's position and Leibniz. They can use the tool brilliantly, but they can't explain why it works. Standing in front of that definition for the first time, trying to pass the nested quantifiers, I remember thinking that mathematics had traded one kind of confusion for another. The infinitesimals were vague but intuitive. You could picture them, even if you couldn't define them. The epsilon-delta definition was precise but opaque. You could verify it, but you couldn't feel it. The confusion was different in kind, and understanding the difference took me weeks of frustration and several conversations with a professor who had the patience to let me arrive at the understanding on my own, rather than handing it to me. The original confusion was about what the mathematics meant. The new confusion was about what the notation said. And I eventually realized that the second kind of confusion is better, because it can be resolved by careful reading, while the first kind couldn't be resolved at all. That distinction between confusion that dissolves with effort and confusion that is permanent is one of the most important things calculus teaches, whether anyone intends it to or not. While the foundations were being rebuilt, the calculus itself was exploding outward, driven by some of the most talented mathematicians who have ever lived. Between the founding generation and the expansion that Euler represented, there was a family that dominated European mathematics like no family before or since. The Bernoulli family, based in Basel, Switzerland, produced at least 8 prominent mathematicians across 3 generations, of whom 2, Jakob and Johann, were among the most important figures in the early development of calculus. Jakob and Johann were brothers, and they were also fierce rivals whose personal animosity fueled some of the most productive mathematical competition in history. They argued about mathematics. They argued about credit. They argued about who was the better mathematician. Johann once entered a competition at the Paris Academy, submitted a solution, and discovered that his son Daniel had also entered and won. Johann was so enraged that he threw Daniel out of the house. Daniel Bernoulli went on to develop the foundations of fluid dynamics, producing Bernoulli's principle, the relationship between fluid speed and pressure that explains how airplane wings generate lift. The principle is named after Daniel, not Johann, which surely would have infuriated Johann further. The Bernoulli family feuds were legendary even by the standards of academic rivalry. Jakob and Johann argued about who had contributed more to the calculus of variations. Johann and Daniel argued about priority in fluid dynamics. The family produced extraordinary mathematics in spite of, or perhaps because of, the constant competition. The rivalry drove each of them to work harder, publish faster, and prove more, in an effort to outdo the others. The family Thanksgiving dinners must have been extraordinary. Jakob Bernoulli, the elder brother, made fundamental contributions to probability theory and to the calculus of variations, the branch of calculus that finds not the value that optimizes a function, but the function that optimizes a quantity. Jakob also studied the catenary, the shape of a hanging chain suspended between 2 points. Galileo had guessed that the shape was a parabola. Jakob proved it wasn't. Using the tools of differential calculus, he showed that the catenary is described by the hyperbolic cosine function, a function related to the exponential rather than to the polynomial. The distinction matters in engineering. The catenary is the ideal shape for arches and suspension cables, and getting the shape wrong means getting the forces wrong, which means structures that sag, crack, or collapse. Jakob studied the catenary, the shape of a hanging chain, and showed that it is not a parabola, as many had assumed, but a distinct curve described by the hyperbolic cosine function. He investigated the logarithmic spiral and was so captivated by its self-similar properties that he asked for one to be engraved on his tombstone with the words "Adem mutata resurgo, though changed, I shall arise unchanged." Johann Bernoulli, the younger brother, was arguably the more brilliant mathematician, but also the more difficult personality. He was vain, competitive, and occasionally dishonest. He once attempted to claim credit for work done by his own Daniel, but his mathematical contributions were extraordinary. He developed the technique of integration by parts, solved differential equations that nobody else could, and trained the young Leonhard Euler, recognizing his talent immediately. Johann became Euler's mentor, and the relationship produced one of the most important teacher-student connections in the history of mathematics. Euler, building on what the Bernoullis taught him, would take calculus further than anyone had imagined possible, extending it to complex numbers, to differential equations, to the calculus of variations, to the number theory, and to virtually every other branch of mathematics that existed in his time. Johann lived until 1748, long enough to see his former students surpass him in both output and reputation. To his credit, Johann seems to have accepted Euler's superiority with better grace than he accepted anyone else's. The relationship between them was one of the few in Johann's life that wasn't marked by jealousy or resentment. In 1696, Johann posed a challenge to the mathematicians of Europe. Find the curve along which a ball sliding under gravity from one point to another will arrive in the shortest time. The problem is called the brachistochrone problem, from the Greek words for shortest time. Johann gave the mathematical community 6 months to solve it. The answer is not a straight line. A straight line is the shortest distance, but not the shortest time, because a steeper initial descent lets the ball pick up speed faster, which compensates for the longer path. The optimal curve turns out to be a cycloid, the path traced by a point on the rolling wheel. The ball drops steeply at first, gaining speed quickly, then curves gently toward the destination, arriving faster than it would along any other path. The challenge was published in the Acta Eruditorum, the leading scientific journal of continental Europe, in January 1697. Johann gave the mathematicians of Europe 6 months to produce a solution, and then extended the deadline when solutions were slow to arrive. 5 people solved the problem: Johann himself, his brother Jakob, Leibniz, the Marquis de l'Hôpital, and, anonymously, Newton. Newton reportedly solved it in a single evening after receiving the challenge, and when Johann saw the anonymous solution, he allegedly said, "I recognize the lion by his claw." The story is probably apocryphal, but it captures a truth. Newton's mathematical style was distinctive enough to identify even without a signature. The economy, the directness, the refusal to show intermediate steps, all were characteristic. The brachistochrone problem opened a new chapter in mathematics. It showed that calculus could be applied not just to curves and equations, but to optimization problems of a fundamentally new kind, finding the best shape, the best path, the best function, rather than the best number. This insight led to the calculus of variations, which Johann's brother Jakob developed into a systematic theory, and which would eventually become the mathematical framework underlying all of classical mechanics. The Brachistochrone problem is significant not just for its elegant answer, but for what it demanded. Solving it required a new kind of mathematical reasoning, optimizing not over numbers but over functions, finding the curve that minimizes a quantity rather than the number that minimizes a function. This is the calculus of variations, and it would eventually become the mathematical framework for all of classical mechanics, reformulated by Lagrange and Hamilton in the 18th and 19th centuries using the principle of least action, the idea that nature always chooses the path that makes a certain quantity, called the action, stationary. The principle of least action is one of the most profound ideas in all of physics. It says that if you want to find the trajectory of a ball, a planet, a beam of light, or a subatomic particle, you don't need to apply forces and compute accelerations at every moment. Instead, you define a quantity called the action, roughly, the difference between kinetic energy and potential energy, integrated over time, and you find the trajectory that makes this quantity stationary, meaning it doesn't change when you wiggle the trajectory slightly. The trajectories that satisfy this condition turn out to be exactly the trajectories that satisfy Newton's laws. The two approaches, Newton's force-based approach and the variational approach, give identical results, but the variational approach is more general, more elegant, and more powerful. It generalizes seamlessly to systems with constraints, to electromagnetic fields, to curved spacetime, and to quantum mechanics. Richard Feynman's path-integral formulation of quantum mechanics, developed in the 1940s, says that a quantum particle takes every possible path from A to B simultaneously, and the probability of arriving at B is computed by summing over all paths, with each path weighted by a factor involving the action. The deepest formulation of physics, the formulation that unifies classical mechanics, electromagnetism, quantum mechanics, and general relativity, is variational. It is calculus of variations, descended from the Brachistochrone problem, descended from the Bernoullis, descended from Newton and Leibniz, descended from Archimedes. The chain runs all the way back. That principle, which grows directly from the Brachistochrone problem and the calculus of variations, is the deepest formulation of physics that we have. It unifies classical mechanics, electromagnetism, general relativity, and quantum field and field, and luretinamide. Every fundamental law of physics can be derived from a variational principle, and that principle traces its lineage back to Johann Bernoulli's challenge in 1696, which traces back to the calculus that Newton and Leibniz created, which traces back to Archimedes filling a parabola with triangles 23 centuries ago. The thread is unbroken. The mathematics accumulates, layer upon layer, each generation building on the one before, each new result opening doors that the previous generation couldn't see. Leonhard Euler, trained by Johann Bernoulli, took the calculus and ran with it further and faster than anyone else in history. He standardized the notation, the symbol f of x for a function, the Greek letter sigma for summation, the number e for the base of natural logarithms, and he applied calculus to problems that nobody had imagined calculus could touch. He used calculus to study the vibration of strings, deriving the wave equation and showing that the solutions are superpositions of sine waves, the mathematical basis of the theory of sound and music. He used it to study the flow of fluids, developing the equations of fluid dynamics that bear his name. He used it to study the paths of light rays through lenses and mirrors, founding the field of geometric optics. He used it to study the rotation of rigid bodies, deriving the equations that describe how gyroscopes precess and how spinning tops wobble. He also made fundamental contributions to pure mathematics using calculus as his primary tool. He proved that the sum of the reciprocals of the prime numbers diverges, a result that shows the primes are more common than you might expect, not as sparse as, say, the perfect squares, whose reciprocals converge. He discovered a formula connecting the prime numbers to the zeta function that Riemann would later extend into the complex plane, producing the most famous conjecture in mathematics. He published roughly 800 papers and books. He went blind in his 60s and his output increased. He is sometimes called the Mozart of mathematics, and the comparison is apt in more ways than one. Like Mozart, Euler made everything look effortless. Like Mozart, he produced an almost unimaginable volume of work. Like Mozart, he was generous with his talent, sharing ideas freely, collaborating widely, and writing with a clarity that made his work accessible to readers far less talented than himself. And like Mozart, his name is everywhere in his field. Euler's formula, Euler's identity, Euler's method, Euler's constant, Euler's theorem, Euler's angles, Euler's line. More mathematical results are named after Euler than after any other mathematician. He is the Mozart of mathematics, impossibly prolific, effortlessly brilliant, and present in every corner of the subject. Euler's most celebrated single result is the identity that connects the 5 most fundamental constants of mathematics in one equation, e to the power of I times pi plus 1 equals 0. The exponential constant, the imaginary unit, the circle ratio, the multiplicative identity, and the additive identity, all linked by a single exact relationship. The identity follows from the more general Euler's formula. E to the I theta equals cosine theta plus I sine theta, which connects exponential functions to trigonometric functions through the complex numbers. It is one of the most beautiful results in all of mathematics, and it is a product of calculus. The Taylor series for the exponential, sine and cosine functions, when extended to complex numbers, reveal the connection. If you are still awake, we're in the final stretch. The foundations are solid, the notation is settled, the feuds are over. What remains is the story of what calculus became once it was free of all that, free of the personal conflicts, free of the logical anxieties, free to be applied to every problem that involves change. And that turns out to be every problem worth solving. We've told the story of invention, Newton and Leibniz. We've told the story of crisis, the infinitesimals and Berkeley's attack. We've told the story of rigorization, Cauchy and Weierstrass. We've told the story of expansion, the Bernoullis and Euler. What remains is the story of what calculus became in the centuries after its foundations were secured, and what it is becoming now. After the rigorization of the 19th century, calculus branched in every direction. The rigorization of the 19th century didn't just shore up the foundations, it revealed new depth in the concepts themselves. Bernhard Riemann formalized the concept of the integral, defining it precisely as the limit of a sum of areas of thin rectangles. Riemann's construction works like this. Divide the interval into subintervals, choose a point in each subinterval, evaluate the function at that point, multiply by the width of the subinterval, and add up all the products. This gives you an approximation to the area. Make the subintervals thinner. The approximation improves. Take the limit as the thinnest subinterval approaches 0. If the limit exists and doesn't depend on how you chose the subintervals or the sample points, the function is Riemann integrable, and the limit is the Riemann integrable. This construction makes precise exactly what Archimedes was doing with his method of exhaustion, filling curved regions with thin rectangles and taking the limit. The conceptual content is ancient, the precise definition is Riemann's, and the Riemann integral is still taught in undergraduate courses today, over a century and a half after its formulation. Henri Lebesgue in the early 20th century generalized Riemann's integral to handle more pathological functions, creating a theory of integration powerful enough to serve as the foundation for modern probability theory and quantum mechanics. Lebesgue's integral can handle functions so pathological that Riemann's integral chokes on them, functions that are discontinuous everywhere, functions that jump at every rational point but are continuous at every irrational point. These aren't mathematical curiosities. They arise naturally in probability and in the study of Fourier series, and Lebesgue's theory is what makes modern analysis possible. The progression from Riemann's integral to Leibniz's integral mirrors the larger arc of calculus. Each generation's tools are powerful enough to solve the current generation's problems, but insufficient for the next generation's questions. The questions keep getting harder. The tools keep getting more sophisticated, and the mathematics keeps growing. Differential equations, y, a function to its own derivatives, became the language of science. This is not a metaphor. It is a literal description of how modern physics, engineering, biology, and economics are formulated. A differential equation doesn't tell you what a quantity is. It tells you how a quantity changes. It says, The rate of change of this thing is related to the thing itself, or to time, or to other quantities in this specific way, and from that relationship you can deduce what the thing actually does over time. Population growth. The rate of change of the population is proportional to the current population. This gives you exponential growth, the foundation of ecology and epidemiology. Radioactive decay. The rate of change of the amount of material is proportional to the current amount, but negative. This gives you exponential decay, the foundation of carbon dating and nuclear physics. Simple harmonic motion. The acceleration of an object is proportional to its displacement from equilibrium, but opposite in direction. This gives you sine and cosine waves, oscillation, vibration, the physics of springs and pendulums, and sound and light. The heat equation describes how temperature distributes itself through a solid object over time. If you heat one end of a metal bar, the heat spreads gradually toward the other end, and the heat equation tells you exactly how fast and in what pattern. The wave equation describes how disturbances propagate through a medium, sound waves in air, seismic waves in rock, electromagnetic waves in empty space. Maxwell's equations, the four differential equations that describe all of classical electromagnetism, predicted the existence of electromagnetic waves traveling at the speed of light, and that prediction, confirmed by experiment, revealed that light itself is an electromagnetic wave. The Navier-Stokes equations describe how fluids flow. They govern the weather, the oceans, the blood in your veins, the air over an airplane wing. They are so difficult to solve that one of the 7 Millennium Prize problems, with a $1 million reward, asks whether smooth solutions to these equations always exist. The equations have been known since the 1800s. The existence question remains open. Einstein's field equations of general relativity are differential equations that describe how the geometry of spacetime is shaped by the presence of mass and energy. Solving them produces the predictions that made Einstein famous: the bending of light near massive objects, the expansion of the universe, the existence of black holes, the slowing of time in gravitational fields. All of this from a differential equation relating the curvature of spacetime to the energy and momentum within it. Newton's second law, force equals mass times acceleration. It relates the position of an object to the second derivative of that position. Maxwell's equations, which describe all of electromagnetism, are differential equations. The heat equation, the wave equation, the Schrödinger equation of quantum mechanics, the Navier-Stokes equations of fluid dynamics, Einstein's field equations of general relativity, all differential equations. The laws of nature, when written in mathematical form, are almost always statements about derivatives. This is not a coincidence. It reflects something deep about how the universe works. The universe doesn't tell you where things are. It tells you how things change. The position of a planet isn't fixed by a law. The law fixes how the position changes, through gravity, through acceleration, through the geometry of spacetime. The temperature of a room isn't fixed by a law. The law fixes how temperature changes, through conduction, convection, and radiation. The universe speaks in derivatives, and differential equations are how we translate. Every time a physicist writes down a law of nature, they are writing a differential equation. Every time an engineer models a system, they are writing a differential equation. Every time a biologist models a population, an economist models a market, or a climate scientist models the atmosphere, they are writing differential equations. And the remarkable thing is that one equations keep appearing in different contexts. The equation describing heat flow through a metal bar is structurally identical to the equation describing the diffusion of a chemical through a solution, which is structurally identical to the equation describing the spread of a rumor through a population. The mathematics doesn't care what the symbols represent. The same equation, the same solution, identical behavior, in metal, in chemicals, in gossip. Calculus reveals the universal patterns hiding beneath the surface of seemingly different phenomena. Joseph Fourier was a French mathematician and physicist who served as a scientific advisor during Napoleon's expedition to Egypt, before settling into a career studying heat. His interest in how heat flows through solid objects led him to one of the most surprising and useful mathematical discoveries of the 19th century. Any reasonable function can be decomposed into a sum of sine and cosine waves of different frequencies. The claim seemed impossible when Fourier first proposed it. How can a jagged function or a function with sharp corners be built from smooth sine waves? The answer is that you need infinitely many of them, and their sum converges to the original function. The convergence is itself a delicate mathematical question that took decades to resolve fully, but the practical power of the decomposition was immediate and enormous. This Fourier analysis, originally developed to solve the heat equation, turned out to be one of the most widely applicable mathematical tools ever created. It underlies digital audio, image compression, medical imaging, telecommunications, and signal processing of every kind. Your phone uses Fourier analysis constantly. When you make a voice call, your voice is digitized, decomposed into frequency components, compressed by discarding inaudible frequencies, transmitted as a digital signal, received at the other end, reconstructed from its frequency components, and played through a speaker. Every step of this process involves Fourier analysis. Your streaming service